Alright, so in this video we're going to talk about equilibrium, which is a special case where all of the torques acting on an object are balanced. And so we get this cool thing where sigma tau, or the net torque, is equal to 0. So let's look at the most common example, seesaw. Draw a piece of wood, the seesaw, and let's indicate its center of mass with this center of mass symbol. If you didn't know, the crash test dummy symbol is the center of mass symbol it is. And then this thing right here is called the fulcrum. The fulcrum is usually like a rock or a little triangle, something that it can balance on. The fulcrum is also the thing that the object is going to rotate around, and so we'll use it to reference all of our torques. For this problem, we're going to say that the board has a mass of m and a length of L. It's very common to use L to represent the length of a board in one of these problems, even if it's not told to you. Alright, so a length L. And let's say that a box is put on the very end of the Seahorse. Alright, now let's say that this box on the edge is also the same mass as the board that has a mass of m. And we want to know where should we place a box that is twice as big, we'll call that 2m, on this seesaw so that it doesn't rotate or that it's balanced. Alright, now to do this we're going to need to indicate a couple of things. First of all, we know that the length of the board is L. Therefore, the radius from the center of the fulcrum, or the center of mass, we're going to call this distance L over 2. So that's the radius that we use when we find the torque from that box of mass m. This 2m box is going to give us some radius or distance. We don't know what it is, so let's call it d. It's the distance from the center. Okay, so the things that are going to be causing torque, or the force that's causing torque, is actually the weight of each of these objects. So there's going to be a weight force down here, which we'll call mg, and a weight force down here, which will be 2mg. Now, the weight of the actual board of the seesaw, or whatever, is actually going to go straight down here. We could write mg there, but it's going to be balanced by a force from the fulcrum that we would call a normal force. And these two are equal to each other. I'll use a double congruent mark. So they're not actually going to contribute anything to the torque on this system. They're also applied at the center of rotation, so the radius of 0 would give no torque. Instead, we're interested in this object's torque and this object's torque. So let's start by looking at the box of mass m that's at a distance L over 2. If I was going to think about its torque is going to be, which let's call this tau 1. Its torque is going to be mg times L over 2. And then if I think about this torque, which I'll call tau 2, it's going to be 2mg times d, which is the distance from the center of rotation. Okay, so here's how we sum the net torques. The sum of the net torques in this case is going to be tau 2, which will make that one positive, why not, minus tau 1. And because it's not rotating, we know that they are equal to 0. That's the main idea. So that means I can set them equal to each other. Tau 2 equals tau 1, or 2mgd equals mg L over 2. Maybe you see how quick it gets now. I don't need m, I don't need g, and if I want to figure out what the distance d is, then I just divide both sides by 2 and get L over 4. So this means I need to place the 2m box a distance of a quarter of the length of the seesaw board, or whatever you're using, which hopefully is a little bit intuitive. Alright, so now let's do a different problem. What if you had this exact same problem, but instead of the fulcrum being placed actually on the center of mass, let's say it's placed just slightly to the left. Okay, so we'll put the center of mass in the middle, and let's divide this board into sixths. So there are 3 of the sixths, and there are the other 3 of the sixths. Okay, so this board still has a mass of m and a length of L. But now what we're going to do is we're going to put the fulcrum here, And our box on the edge, we're going to make it a box that is 3 times as massive. We'll call it 3m. Oh, sorry. We'll call it 3m. God, this is great. And we'll say that it is a distance of 2L over 6th, which, of course, you could write that as L over 3. Now, this, the center of mass, is going to be 1/6, or L over 6th, away. And what we're going to try and do is figure out where we should put a box of m, a box of mass m, on this, a distance of d, we'll write it like that, away from the fulcrum, or the point of rotation. Where should we put that box? All right, so in this problem, there are 3 forces that cause torque. There's the weight of the 3m box, 3mg. There's the weight of the actual board itself, which we'll call mg, and then there is the weight of this box that we're trying to figure out where to put, which will have the same weight as the board itself. Now, each of these forces are applied at different radii, L over 3, L over 6, and this mysterious distance that we're trying to find. So we can create torques for each of those forces. Again, the idea for this problem is that the net torque is 0. And if you can see it, these torques on the right, those are torques that are going to try and rotate the object clockwise. This torque on the left is going to try and rotate it counterclockwise. So let's make the counterclockwise torque negative and the clockwise torque positive. You could do it either way, it doesn't really matter, because they're going to add up to 0. And let's call this one tau 1, tau 2, we'll call this tau 3. Okay, so basically I would add the 2 clockwise torques together, T1 plus T2, and then subtract the counterclockwise, T3, and they add up to 0, which is just to say that they're balanced. And so I could add tau 3 over to the right, and now I can start to plug in what each of these torques are be. Tau 1 is going to be mg times its radius, which is L over 6, so that's going to be mg L over 6. Tau 2 is going to be mg times this distance that we want to find, so we'll call that mgd. And tau 3 is going to be 3mg times its distance, L over 3. So 3mg L over 3. Okay, so now let's do some simplifying. Hopefully you see that mg is actually not needed because there's an m in every term, there's a g in every term, and 3L over 3 is just L. So this is like saying L over 6 plus this distance we want to find is equal to L. Or the distance is equal to L minus L over 6, which is 5L over 6. So you now know that the distance you need to put that box is 5/6 of the length of the board away. All right, now let's do one last problem. This is going to be a problem that involves a sawhorse, which if you've never seen a sawhorse is basically something that you use to support a saw, or sometimes you put a piece of wood on the sawhorse so that you can cut it in half. Yeah, that's a sawhorse. In this case, let's put a piece of wood. Oh, that's a great. I'm doing great drawing my boards today. Okay, so let's draw your sawhorse right there, and we're going to put 2 sawhorses, one at the very end, we'll call that sawhorse A, and one, let's say, I don't know, 2/3, maybe that's a third, let's put the sawhorse right there. So this distance is 2/3 of the way over, and we'll call this sawhorse B. All right, so for this problem, there are going to be 3 torques. There's going to be a torque at the center of mass from the weight of this board, which we'll say it has a mass of m and a length of L. So mg acts down at the center, and that happens halfway through, so I could call this distance L over 2 if I wanted to, but for right now let's save that conversation for when we talk about where the point of rotation is. The other 2 forces are going to come from the sawhorses. They'll support the object by acting up, so we'll call that a normal force acting on A, and this we'll call a normal force acting on B. So we'll call this one NA, and we'll call this one NB. Okay, so for this problem, the net torques are going to add up to 0, and here's where we have this really interesting choice. Whenever the object is not rotating and there's not a clear center of rotation, you can pick it. Like, you can pick where you want the center of rotation to be. I'm going to pick right here to be our point of rotation. We'll call that the pivot, because it's a little bit easy for us to see it. So by doing this, what I'm effectively saying is that no torque is generated from the normal force, NA. Instead, only the weight and the normal force from B is going to give any sort of torque to this system. So let's do that. Let's net the torques. I know that the torques add up to 0. And in this case, I'm going to have a torque from NB, which is at a distance of 2. So if I want to find the torque here, we'll call this torque B. That's going to be the normal force times the distance from the pivot, which is 2L over 3. Okay, so NB times 2L over 3 is that torque that's going to try and rotate the system counterclockwise. Now, it's going to be balanced by the torque from the weight, which is put at a distance of, if you can imagine, just L over 2. So we know that that force is going to be mg L over 2. All right, now this alone is not enough information to figure out. Let's say we wanted to say where to put this second sawhorse right here, B. Or I'm sorry, I mean, let's say we're trying to figure out how much of the weight is supported by that sawhorse at B. That wouldn't necessarily be enough for us to figure it out, because we would need to know what the length of the board is. But instead, we can think about the net force in the y direction, because all these forces are pointing up or down. And I know that those forces are also balanced. So that would say NA plus NB equals, minus mg equals 0. Or we're effectively saying that NA plus NB, not M, equals the weight, mg. So from this, I could say something like NA equals mg minus NB. And since I know that NB is going to be equal to, we can cancel out the L. There we go. And we can cancel out this 2, 3. No, we can't cancel out that 2. Why didn't you stop me? 3 mg over 4. There we go. I can now plug that in and figure out that NA is equal to mg minus 3 mg over 4, which is simply a fourth. All right, so let's take a look at what we've just found here. By putting these sawhorses at the far edge and then 2/3 of the way down the length of the board, we now know how much of the weight is supported by each sawhorse. Sawhorse B supports 3/4 of the weight. Sawhorse A supports only 1/4 of the weight. Congratulations, you've done pretty much all of the equilibrium problems that you need to do to be successful on your assignment. Yay, you're so smart. Good job.